Assalamu alaikum students. Today's topic is going to be about simple harmonic motion. Simple harmonic motion. Let us consider a mass attached to one end of an elastic spring which can move freely on a frictionless horizontal surface as shown in figure. For explaining that, let us consider an example. Here we have a mass. Let's say that we pointed out that this is the mass which is M, which is attached to a spring and which is on a frictionless surface. Now, when the mass is displaced towards the right through a distance x, that means it is moved to the right side of the screen to the distance of x, the force Fx at the instant is given by Hooke's law. What was the Hooke's law? F is equal to Kx, where K is a constant known as spring constant. That means this spring, how much can it sustain a force on it? Due to elasticity, the spring opposes the applied force which produces the displacement. Now we are applying some force. This force which we are applying, we call it applied force, which is represented by F. Now, if we apply the force, let's see what happens. It moves a distance x towards the right of the screen. Now, what happens? There is an elasticity in the spring, which will possess it to return back to its original or equilibrium position. The opposing force is called restoring force. That means now the spring is applying a force on this mass, which is called restoring force, which is equal and opposite to the applied force within the elastic limit of the spring, which is given by Hooke's law. Restoring force is equal to minus kx, where k is the spring constant, x is the displacement, and Fr is the restoring force. Now, if we apply the force is in the direction negative to the applied force, that means the opposite direction, but the displacement was in this direction. As you can see, the restoring force and the displacement both are in opposite direction. In physics, we know the opposite direction is represented by negative sign, and that is why there is a negative sign in the equation also. Now, it will return from its original position, but due to inertia, it moved back a little bit. That was its original position or equilibrium position, but it moved back. And it will keep on doing so because of its inertia and simple harmonic motion. So, we can see right over here, it passes through that point, that particular point, many times. Now, that is according to the spring. Now, if the spring is increased like this, or when it restores like this, it will keep on oscillating about its mean position. Now, how can we define the simple harmonic motion? The negative sign indicates that Fr is directed opposite to the x towards the equilibrium position. Thus, we can see in a system obeying Hooke's law, the restoring force is directly proportional to the displacement. Yes, it is directly proportional. That means more we apply force over here, the displacement from that direction will be in the same manner of the displacement, directly proportional to the displacement of the system from its equilibrium position, and is always directed towards it. When a mass is released, it's being oscillated about its equilibrium position, just like I showed you. Now, in this case, let us define the simple harmonic motion. The oscillatory motion taking place under the action of such restoring force is known as simple harmonic motion, or in abbreviation form, it is SHM. The acceleration A produced in the mass m due to restoring force can be calculated by using the second law of motion, which was F is equal to ma, or in words, if you want to speak it, when a force is applied on the body moves in the direction of the force with some acceleration. Now let us compare these two formulas. Let's call this equation number 1 and this is equation number 2. Both of them are equal to force. Let's put them equal to each other. ma is equal to minus kx. So, if we rearrange the equation, it will be minus kx over m into x. Now, in this case, both K and M, both are constant values. This one is spring constant, and as you know, mass is constant throughout this procedure. Now, if we remove these constant values, what we are left with? We are only left with acceleration, which is directly proportional to displacement, but in opposite direction. That is why the negative sign is there. Let us read about it. Thus, if we rearrange the equation, these two equations, and we got minus ks equal to ma. From that, we rearrange to get a is equal to minus k over m into x. From that, if we remove the constant value, we are only left with proportionality. That means a is proportional to minus x, and the negative sign is showing that it is moving opposite direction to the acceleration. The acceleration at any instant of the body executing SHM is proportional to displacement and is always directed towards mean position. That means always move towards its mean position. Either it is coming from here or here. Now, in this case, let us define a summary version of simple harmonic motion. Simple harmonic motion occurs when the net force is directly proportional to the displacement from the mean position and is always directed towards the mean position. That means F is directly proportional to displacement. In other words, when the object oscillates about a fixed point mean position such that its acceleration is directly proportional to its displacement from its mean position is always directed towards the mean position, and its motion is called simple harmonic motion. So in this case, we already learned that A is also directly proportional to x but in opposite direction. Now, what are the main features of this simple harmonic motion? Now, let us look at this situation in which we have mass attached to a spring system and was applied by a force. It showed a body executing SMGM it always vibrates about its fixed position. That means it will always return back to its mean position or equilibrium position. It accelerates always directly towards the mean position. That means it always will come back accelerating towards its mean position. Because of inertia, it will go ahead, but it will always return back to its mean position, or you can say mean position or equilibrium position. Now, if we extend it, as you can see, the velocity over here was constant, but it stopped over here at the extreme position. That means at the extreme position, the velocity is constant, but over here, acceleration will be maximum because at this point, extreme point is stopped, and then it tried to return back to its mean position, just like this. But at the mean position, as you can see, the velocity was maximum, and as the velocity was maximum, the acceleration was zero because velocity was constantly moving at the mean position. But at extreme position over here as well, the velocity will again be zero because it has to change its direction, and acceleration again will be maximum at this point, and you can see it will move back towards the mean position. So how to explain this whole phenomena? The magnitude of acceleration is always directed towards its displacement from the mean position. That is, acceleration will be zero at the mean position. That means at the mean position, acceleration will be equal to zero, while it will be maximum at the extreme position. That means acceleration will be maximum at extreme position on one side as well as extreme position on the other side of the oscillating body. Now for the velocity part, its velocity is maximum at the mean position and zero at the extreme position. That means its velocity is going to be maximum at the mean position, whereas minimum, or you can say velocity, will be zero at the extreme position, like over here and over here. I hope you understood today's lecture. Inshallah, we'll meet again. Allah.